Hi, my name is Elvis from Hanyang University in Seoul. Today, my presentation will focus on a self-healable mechanosensitive e-skin approach that we have actually been able to realize for Iontronic wearable sensors. So first of all, over the years, there has been an increase in investment on e-skin that imitates the mechanosensory system of the human skin. So actually, the mechanosensory system converts forces acting on the skin into electrical signals that can be detected by the human brain. So this actual system has been incorporated into artificial materials, especially polymers, to design electronic skin that can actually detect mechanical stimuli such as pressure or strain. So the e-skin market size is expected to increase with a growth rate of 38.7% over the next 5 years. So there's been an actual increase in investment due to the application of e-skin in soft robotics, in prosthesis, soft interface, as well as wearable technology. So to understand the basic mechanism of how these types of e-skin works, we first have to look at the mechanosensory system in the human skin. So the mechanosensory system actually detects forces that act on it by the pumping of ions from the extracellular region of the cell into the intracellular region in response to external mechanical stimuli such as pressure. So this ionic movement has actually inspired the concept of iontronics in polymers. So what is iontronics? So here we can see that iontronics combine ionics as well as electronics in the process to regulate the electronic properties of materials via ion dynamics. So here, ions has been introduced into polymer matrix, and then when there is a mechanical stimuli, these ions have been pumped to the electrode-electrolyte interface to actually generate EDA capacitance change. This is in response to any mechanical stimuli such as pressure. So this type of system has merit due to these following advantages that are very crucial in the development of tactile sensors. So, however, the main drawback of iontronic systems is that these materials are usually fabricated from soft materials due to ensure effective pumping of ions under deformation. So, because these materials are from soft materials, they are vulnerable to unexpected mechanical damages, which lead to broken functionalities as well as device failure. So, self-healing properties have been introduced into iontronic systems to ensure that it can restore its functionalities even under unexpected mechanical damages. And then this also leads to high stability as well as increased lifespan of the devices. However, there are still some challenges that still persist. So we consider these systems usually have low device sensitivity due to the high initial capacitance value, and also it has a slow self-healing speed at room temperature. So what we have done here is to be able to successfully achieve higher sensitivity together with high self-healing speed at room temperature. So our main concept is by the introduction of chlorine functional group into the TPU matrix together with iron liquid. So what happens is that the ions due to the chlorine functional group actually interact with the ions in an Ion-Dipole interaction to actually generate ion confinement effect. So for the ion confinement effect, when there is no stimulus, these ions are trapped to the chlorine functional groups, and then under stimulus such as pressure, the ions are being pumped to the electrode-electrolyte interface that increases the EDA capacitance change. So this ion trap and release concept actually ensure that we have higher sensitivity in our system. For the autonomous self-healing concept here, we have high chain mobility IPDI, and as well as dynamic disulfide bonds in the backbone of the TPU. This ensures that we have higher self-healing speed at room temperature. So for the material analysis here, to actually determine the optimum amount of iron liquid needed for effective device fabrication, we introduce different concentrations of iron liquid into our system and analyze its mechanical property. So we can see that from the UTM data, the Young modulus decreases as the iron concentration also increases. So on the other hand, we can see that with higher ion concentration, the ion conductivity increases. So here there is some trade-off relationship. If we have high ion concentration, this will affect the elastic recovery, which is not good for a device fabrication. On the other hand, if we have lower ion concentration, this also means that we have lower ion mobile ions, which will also affect the sensitivity of our device. So in all, we chose a 38% concentration for any effective device fabrication, and we analyzed the self-healing properties of our material. So you can see that we're able to achieve 91% self-healing efficiency at room temperature, which is quite high compared to other self-healing dielectric materials at room temperature. So to actually analyze the ion confinement effect in our system, we also did a stress realization test on our samples. So here we have a sample without any chlorine functional group, and we have sample with 58% chlorine functional group. So we can see that even as the pressure increases, there isn't any effective change in the sample without any chlorine functional group. However, you can see that the bulk resistance actually decreases as the pressure increases. This actually indicates that more ions are being pumped as the pressure increases, and this leads to the reduction of the bulk resistance in the sample with chlorine functional group. You can also see that the charge realization frequency also shifts towards a higher frequency, which also indicates that more ions are being pumped, and then this increases the ion dynamics in our system. So you can see that from the realization time graph, as pressure increases, we have free ion density, high free ion density, due to the point that the realization time also decreases, and then this is due to the fact that the ions that were initially trapped are being released as the pressure increases. So for some device performance here, we have a comparison between samples. First, we have 3 samples here, samples without any chlorine functional group, and then with 50% chlorine functional group, as well as 78% chlorine functional group. So as the content of chlorine functional group increases, the response to static pressure also increases, as you can actually see here. So this is quite effective. However, we actually focus on 58% chlorine functional group because higher chlorine functional group also affect the self-healing speed of our system. So we chose only 58% for any device fabrication. And as I mentioned earlier on, you can see that at initial state, we have a lower initial capacitance voltage, and then as we have as maximum pressure, you can see that the capacitance, the final capacitance value also increases. So this change in capacitance actually ensures that we have a higher sensitivity, which is quite good for any device fabrication. So we can also see that from the impedance spectroscopy, our system has a reversible ion movement. This is also very good for the device stability. And then from the transient response, you can see that our device can adapt to different pressure conditions. And then we can also see from the graph here that at lower voltage as well as at lower pressure, we can actually detect the response as well as the reset value of our system. So in conclusion, we have described here a novel design approach to achieve a reversible ion confinement effect in a homogeneous composite together with autonomous self-healing at room temperature. We are able to achieve this through the introduction of chlorine functional group together with ions via Ion-Dipole interaction. So the higher self-healing speed was possible due to the high chain mobility of IPDI as well as the dynamic disulfide bonds in the backbone of the TPU. And then here our device was able to achieve reversibility with high sensitivity due to the reversible movement of ions that actually ensure fast response as well as reset rates. So what we can say here that we believe that this work provides a new insight into developing self-healable pressure sensors with high sensitivity for wearable sensors in the future. So acknowledgement to my professor Dong Kim in Hanyang University, and then to my lab mates who has contributed immensely to this project and then to the National Research Foundation program. Thank you very much for your attention.
Thank you very much for your wonderful talk. And 혹시 질문 있으실까요?
Thank you for your talk. I was just wondering, after the self-healing process, then the pressure sensitivity.
Okay, so we are yet to actually do an institute test for the pressure sensitivity after the self-healing. So right now, we haven't done the institute, but then there isn't any much difference in the sensitivity after the self-healing because we have about 91% self-healing efficiency and then the ions are able to actually move into the EDL, the electrolyte interface to generate effective EDL formation.
혹시 더 추가 질문 있으실까요?
Thanks for your inspiring presentation. I have one question about your presentation, and it's about you said about the self-healing properties of this material, right? And I just wondering, somewhere on the surface, possibly damaged, and then possibly on the other side could have been crack or wrinkle after all. So did you see the before and after of this overall shape?
So because we introduced the chlorine functional group, and then in the TPU structure we had a hard segment as well as a soft segment. So these components ensure that we have a good elastic deformation property. So there isn't any much of wrinkles or in terms of crack, unless there is, we crack it by ourselves, which is means that we are doing the self-healing test. So besides that, any micro cracks are really negligible because of the hard segment and the soft segment components in the TPU mattress.
혹시 추가 질문 있으실까요? 없으시면 다시 한번 좋은 발표를 해주신 연사에게 다시 한번 큰 박수 부탁드리겠습니다.